Okay, in this in this video, I'm going to go over some of these practice problems, and we'll start with this one here. And to make a decision for a problem like this one, we need to assign values to each of these outcomes. So we'll do that by first taking these. So we start with these preferences. Espresso machine is preferred to the Nintendo Switch. The iPad is preferred to the espresso machine. The vacuum is preferred to the TV. The dishwasher is preferred to the grill. The agent is indifferent between the laptop and the TV. The agent is indifferent between the vacuum and the grill. Prefers the grill to the laptop and is indifferent between the TV and the iPad. So we want to rank these in order of those preferences. So, espresso machine, switch, iPad, espresso machine, vacuum, TV, dishwasher, grill. Okay, so let's start with the dishwasher is preferred to the grill. The grill is preferred to the laptop. The agent is indifferent between the grill and the vacuum. The agent is indifferent between the TV and the laptop. The agent is indifferent between the TV and the iPad. So let's see, we've done this one. Dishwasher and grill. iPad is preferred to the espresso machine, so the espresso machine has to be down here. The vacuum is preferred to the TV. Okay, we actually already have that one figured out. And the espresso machine is preferred to the switch. All right, let's actually move these. Okay, and then to assign utility values, we're just going to start with the lowest valued one, which is the switch. Give that a 1. Give the espresso machine a 2. Everything on this line, which are things that the agent is indifferent between, is valued at 3 on our scale. Grill and vacuum are both 4, and the dishwasher is 5. Okay, now we just need to create another decision table, bet 1, bet 2. Okay, so espresso machine and grill. Okay, so the espresso machine we said is valued at 2. The grill is 4. iPad and laptop. The iPad and laptop are both 3. The vacuum and the switch. The vacuum is valued at 4. The utility value for the vacuum is 4. For the switch, it's 1. And then TV and dishwasher. TV is 3. Dishwasher is 5. Okay, there we go. Now, okay, so we created the decision table with utility values. Now we need to use the maxi-min rule to make a decision. And so to use this rule for each option, that is each row, we need to find the minimum value, minimum valued outcome. So for bet 1, looking at this row, the minimum is 2. For bet 2, the minimum is 1. Okay, so those are the minimums that you can end up with, or the minimum valued outcomes that you can end up with if you choose bet 1 and bet 2. And the maxi-min rule tells us to pick the option that is associated with the higher of the two. So we're going to pick bet 1. If we choose bet 1, the worst we can do is get an outcome that we value at 2. If we choose bet 2, we have a chance of getting an outcome that's valued at 1. We might do better. We might get one of these other outcomes, but if we choose bet 1, we're minimizing how poorly we can do, how badly we can do. Okay, so following this rule, we would choose bet 1. Okay, for this one, we're going to use the dominance principle. So to do that, we first compare bet 1 and bet 2. So we're not thinking about anything going on in bet 3 right now. We're just looking at bet 1 and bet 2. And first, we'll consider what happens if red is drawn. If we're here, so if red is drawn, we'll get 1 outcome valued at 1 if we choose bet 1, and an outcome valued at 4 if we choose bet 2. So 4 is better. If blue is drawn, we'll get an outcome valued at 6 if we had chosen bet 1, and an outcome valued at 3 if we had chosen bet 2. Okay, so bet 1 does better there. Here, bet 1 does better again. Here, bet 2 does better. Okay, so between bets 1 and 2, sometimes bet 1 will do better, sometimes bet 2 will do better, so neither option dominates the other. Okay, so nothing going on there. Between bet 2 and bet 3, so now we're not looking at bet 1. If red is drawn, bet 3 does better. If blue is drawn, bet 3 does better. If yellow is drawn, bet 3 does better. And if green is drawn, they do the same. Okay, so no matter what happens, if you choose bet 3 instead of bet 2, you'll do as well or better. So bet 3 dominates bet 2, and so we want to eliminate bet 2 as an option. Now, between bet 1 and bet 3, if red is drawn, bet 3 does better. If blue is drawn, they do the same. If yellow is drawn, bet 3 does better. If green is drawn, bet 3 does better. Okay, so bet 3 also dominates bet 1. Okay, we eliminate bet 1 as an option or as a viable option, and so that leaves us only with bet 3. So in this case, we would choose bet 3 using the dominance principle. For this decision problem, first apply the dominance principle. If the dominance principle doesn't yield a single best option, use the maxi-min rule to make a decision. All right, so I will just tell you, let's see, do a quick check here. Okay, so no option dominates any other in our decision problem. So, I mean, you should check that yourself, but let's just go on to using the maxi-min rule. So again, for each option, that is for each row, we want to find the minimum valued outcome. So for bet 1, that's going to be 3. For bet 2, that's going to be 1. And for bet 3, it's going to be 2. All right, so the maxi-min rule tells us to pick the option that's associated, that gives us a chance of getting the highest of these minimum payoffs. Okay, so that's going to be the highest of our minimums is going to be this 3, and we would choose bet 1. All right, and that's not to say that we want to get an outcome valued at 3. We'd prefer to get, well, in this case, 8. But when we're using, the idea behind using this rule is that we want to minimize how badly we can do. All right, so that's similar. Let's look at this one. Okay, so for this decision problem, first apply the dominance principle. If the dominance principle doesn't yield a single best option, use the maxi-min rule to make a decision. All right, so again, let me just check. Okay, so no option dominates any other option here. So we'll just go on to using the maxi-min rule. So for option 1, the minimum valued outcome is 3. For option 2, negative 3. For option 2, it is also negative 3. For option 3, it is negative 5. And for option 4, it is negative 3. Okay, so our goal here is to choose the option with the highest minimum, but we have a three-way tie for the highest minimum. So what we're going to do is eliminate the option 3 from our options. And then we're also going to take these off the board. And look for the next highest minimum for each option. So for option 1, now that we're just looking at these 3, the minimum is negative 2. For option 2, looking at these 3 outcomes, the minimum is negative 1. And for option 4, it's again negative 1. Okay, so again, we have a tie as the highest of these minimums at negative 1. So like we did last time, we will eliminate option 1 and stop looking at these. Okay, so now for option 2, we're looking at 2 and 1. 1 is the minimum. For option 4, we're looking at 0 and 4. 0 is the minimum. Okay, so now we can pick the option that has the highest of these minimum values, which is going to be option 2. All right, so we had to eliminate some ties, but using this rule, or using the version where we eliminate ties, we choose option 2.